As you can see from the title of this lesson, this is a tutorial on the ideal gas equation. In this chapter, we have been working with a variety of conversions that lead us to different properties about gases such as density, molar mass, molar volume, plain old-fashioned mass, and plain old-fashioned volume of these various gases. The ideal gas equation is a particularly useful equation because it allows us to account for properties of gases at any conditions. This includes the number of molecules. A lot of the problems that we've been doing, especially as we get to non-STP conditions, have us doing combined gas law problems to get volumes at STP so that we can use the 22.414 conversion that we've been working with. The ideal gas equation is useful in the fact that it will let you find a volume in any set of conditions, right? And you can use that to get things like molar mass, volume, density. The ideal gas equation states PV equals nRT, where in this case P stands for the pressure, V stands for volume, T stands for temperature, N represents the amount, and R is a constant. The only tricky thing about the ideal gas equation is that it has to have very specific units as you go through. Pressure has to be in atmospheres. Volume must be in liters. Amount must be in moles. Temperature, no surprise, must be in Kelvin. The reason for that is how we have to cancel units within this constant R. Right? And the gas constant R, the ideal gas equation constant, is 0.0821 liters ATM per mole Kelvin. You can simply remember that number, but let's talk about for a moment how that number came to be. Finding R. If I were going to analyze a gas, I would try to use the most logical relationships that we have for finding these gases. If we were looking at the equation, PV equals nRT, and I were solving it for R, I would divide both sides by N over T. If I were going to choose an amount of a gas to work with, right, I would choose 1.00 moles. Reason for that is it's the standard amount of a gas that we have many, many relationships to. For instance, if we have 1.00 moles of a gas, we know that it takes up 22.414 liters of space. This holds true so long as we are at STP, which would be 1.00 ATM and 273.15 Kelvin. If we plug these into our expression for R, you would get 1.00 ATM 22.414 liters over 1.00 mole divided by 273.15 Kelvin. Sure enough, if you were to type all of that into your calculator, you would get 0.0821. And notice, none of these units cancel. Liters, atmospheres, mole, Kelvin. That is why the unit is so complex. Because the constant carries those 4 units, our other variables in the equation must share those units so that they'll cancel. That is why pressure is in atmospheres, volume is in liters, amount is in moles, and temp is in Kelvin, because they will not cancel with the other units in the constant unless we do them. So let's take a look at some instances where we can use the ideal gas equation. And the great part about it is, if you are not comfortable with doing things the bracket problem way, the ideal gas equation offers you a different method of solving that perhaps makes more sense. If you open up the ideal gas equation overhead, which is in the notes section of your headline handout, you will see that number 1 says, what is the pressure of a 0.500 mole sample of a gas if it occupies 10 liters at 25 degrees Celsius? We've been doing a lot of problems with finding volumes and moles and things of that nature to get grams over moles and grams over liters. I first wanted to just show you how the equation works, and then from there we can start to use it on things that look more similar to what we've done. So, the question says, what is the pressure, which means I am looking for atmospheres. It tells me I've got 0.500 mole of a gas. It tells me it is 10.0 liters, and that's at 25 degrees Celsius. Where a problem like this would start to explain things is we always express volumes, like liters, as having a certain temperature and pressure associated with it. This problem would let me find what is the correct pressure if for this amount of a gas at these 2 conditions. What would be my third condition? So if you take a look, you'll see I have moles, volume, temperature, and I'm looking for pressure. All of those lead me to wanting to solve the ideal gas equation. We are looking for pressure, so to get that by itself, I will divide both sides by V. Therefore, pressure equals nRT over V. In the past, we always ask ourselves 2 questions. Do my units match, and is my temperature in Kelvin? When we've done it before, we were checking to see if our V1s and V2s and P1s and P2s matched. We can still use the same phrase though. The only difference is, when I say do my units match, I mean do my units match the units that are in the constant R. And my temperature still needs to be in Kelvin. Right, so do my units match? Right, I need to have moles in moles, we are good. I need to have volume in liters, we are good. I need to have temperature in Kelvin, we're not. So the first thing I'll do is add 273.15, leading this to 298 K. Notice, I stopped that at the 298 because 25 stops at the decimal point. I cannot go past it. So now my units are in the correct form. I'm ready to plug in and solve. N is 0.500 moles. R, 0.0821 liters ATM per mole Kelvin. T, 298 Kelvin, all over V, 10.0 liters. Take a look at your units first. Moles cancels, liters cancels, Kelvin cancels. Only unit I'm left with is atmospheres. From here, I'm just plugging it into my calculator. 0.500 times 0.0821 times 298 divided by 10.0. My calc says 1.223. I only get 3 sig figs though, and the 0.0821 will limit you. So with 3 sig figs, I would say I need a pressure of 1.22 atmospheres to make this volume of gas stay at 10 liters under those conditions. Example number 2 says, what volume will be occupied by a 168 gram sample of butane at 43 degrees Celsius and 780 mmHg? Here's a problem that more closely relates to what we have been doing in class. We try to find volumes a lot because we can use them for densities. We can use them for molar volume. We can use it for just predicting an amount of volume that we will get. So, if we take a look at this problem, question says, what volume? So we are looking for liters. It tells us we have a 168 gram sample of butane, which is C4H10. That is at 43 degrees Celsius and a pressure of 780 with no decimal point mmHg. So, you would find out that if we did this using the combined gas law way, that it would be very long, because the first thing I would do is convert the grams of the substance into moles. Then I would use the 22.414 to convert it into liters at STP. We are not at STP, so then I would have to go and change my conditions from STP to not STP conditions to get myself the liters at that particular set of conditions. The ideal gas equation is great in the sense that it allows you to do all of that in half the time it would usually take. Ideal gas equation, PV equals nRT. This time I need liters, so I'm solving for volume. Divide both sides by the pressure. I would get that volume equals nRT over P. Before I can plug in, I have to make sure, do my units match? Is my temperature in Kelvin? So, my N needs to be in moles. It is not. So the first thing I need to do is convert grams of C4H10 into moles. We've done that a lot this year. It's a one-step bracket problem. Grams on the bottom, moles on the top. One always goes with moles, and then I go to the periodic table to get the mass of C4H10. So I take 4 times carbon, which is 12.01, plus 10 times hydrogen, which is 1.008. That leads us to a number of 58.12. Grams will then cancel, getting ourselves a number for moles. 168 divided by 58.12 looks like 2.8905 with 3 sig figs, 2.89 mole. R is the constant, 0.0821 liters ATM per mole Kelvin. Temperature must be in Kelvin. Again, it is not. It's in Celsius, so we add 273.15 to our 43. Looks like we get 316. Again, 316 stops at the decimal because 43 stops at the decimal. Apologize about the writing getting small there. Last but not least, my pressure. My pressure has to be in atmospheres. It is not, it's in mmHg. So you have to do a conversion to get it into ATM. If you remember, 1 ATM has 760.00 mmHg. Because we only get 2 sig figs, this number ends up being 1.0 ATM when you take the 780 divided by the 760, because you only get 1.026 with 2 sig figs, that's 1.0 ATM. Now you just finish out the problem by doing your math. Atmospheres cancels, moles cancel, Kelvin cancels, this time leaving me with liters. Plug these numbers in. 2.89 times 0.0821 times 316 divided by 1.0. I only get 2 sig figs, so I would have to call this 75 liters. And that 75 liters is at our conditions. So even with a couple conversions to plug into this equation, I still believe this to be faster than the combined gas law version, where you have to do not only a bracket problem like we are doing now, but you add on top of it a long drawn out combined gas law. P1 V1 T2 equals P2 V2 T1. The third problem says, find the pressure exerted by 8.789 grams of nitrogen if it occupies 325 milliliters at 74.25 degrees Celsius. This is a good one to practice to see if you are on the right track. The one thing I will say is don't forget that nitrogen is a Hoberfinkel, N2. So when you go to convert your grams into moles to plug in, you have to remember that to take 2 times the mass off the table for this step right here. If you do that problem correctly, you end up getting an answer of 27.5 atmospheres. So give that a try, see if you can get yourself to the right answer. Right? Hopefully you can, and hopefully that everything up here has helped you out with your ideal gas equation. If you're still struggling, please come in for some help and we'll get you sorted out.